In the context of previous presentations that we see biology is so complex, we still scratching the surface trying to understand. And there are not enough scientists in the world to do it. And if we can have some AI help, that would be probably a good thing. So my presentation about reflecting on automation of science, history of it, where we are with it now, how much we can automate now, and where we're probably heading towards. No, before we start, just some thoughts. So we all agree that computers are just great dealing with big numbers, so they now generate interesting, if not completely truthful text. And today just was a celebration of creativity, so they are getting more and more creative. But what is going to be next? So in my view, the next big step will be when we will be able to consume more knowledge. So not just data, but if we start using what we know. And so the next stage will be knowledge and reasoning intensive systems. And the systems that do scientific discovery is within this category. So I would like to give that quotation. As you see, it's quite old. It's by pioneers in this area, automated scientific discovery. It's actually around for more than half a century. And this is the knowledge principle that the principle asserts that specific knowledge is the major source of machine and human intelligence and will suffice even with simple inference. So just to stress the importance of knowledge, and that is why I believe that is the next critical step. Again, to reflect on what is happening right now. So if you take an AI system, it's mostly taking lots of data. In the best case, it will take lots of different data, put it together, and then it outputs some predictive model or something else, or I don't know, piece of art. But knowledge is still hugely underused. No, one reason there is not much available in forms that computers can consume. But just imagine if even these new models were immediately fed back and could be an input, so it's called closed-loop systems, and probably it would be more intelligent. So what I'm talking about is focusing on systems that actually producing something new. It can be a new knowledge model, or it can be updated. And such system to really produce something significant, something new, what we didn't know enough, data is probably not enough. So you need to consume more and more knowledge. You still need data, and if you can put it all together, and quite obviously, the more system knows, the more intelligent behavior it can exhibit. So the first such system considered to be Dendral. It was developed in the 60s in Stanford University. It was inspired by a mission to Mars, that these rovers will collect samples, unknown substance, what it is, so it's they cannot take a lot back to Earth. They cannot really send data because it will take so long. So this was an inspiration to create something very intelligent that can try to get these chemical structures, so to analyze these results immediately. And this system, so it was taking a lot of data. It's different. It could do mass spectrometry. I'm not a chemist, but quite advanced ability. So what experiments with these samples it could do. But what was interesting, the developers worked a lot on trying to formalize knowledge about chemistry, what expert knew at that point. They spent months and months before systems started really produce something comparable what chemists would do. And they put in place a whole pipeline, knowledge acquisition, also giving output in form that is good for users, in this case chemists, and it really produced very interesting, promising chemical structures. Moreover, the system actually was multi-agents. It was heuristic dendral, method dendral, and it was closed loop. So whatever it managed to discover, it immediately was going back and improved over time. So it was 60 years ago, and I would claim we haven't progressed much further. Of course, there were other fantastic systems, but the underlying architecture and principle how it operates is still the same. Just very briefly, another example, because it's a very different system, Bacon, it mostly worked with data and, yes, knowledge of chemistry and physics, and this system was able to rediscover laws of chemistry and physics, so it was also very impressive. And one of developers, Pat Landley from Stanford University, he listed in his review examples of other such discovery systems that discovered true scientific knowledge. And what I would like to talk about it is this last line, what he listed. So this is projects that we have been working ever since. So it's called the Robot Scientist. And this was introduced again 15, 20 years ago now. So the idea is to develop a system, AI system, that is capable of generating hypotheses, designing experiments, having real robotic labs to carry out these experiments, analyze results, do it in cycle, and hopefully discover something new. And when the first system, surprise, it was called ADAM. Actually, it stands for Adaptive Machine and blah, 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 but it was ADAM. When it first actually discovered something new, gene functions, it made a lot of splash. And since there were several such systems, there were many discoveries, and it gained popularity. But the underlying principle is the same as 60 years ago. So it's a lot of data, external data, whatever data sets are relevant, plus internally produced, because it's a robotic lab, very powerful, that can run in parallel, like 1,000 biologists working in parallel in that lab. But it also has this knowledge, formalized knowledge. It has domain knowledge. The first system worked with yeast biology, but it also had this knowledge about what scientific discovery is, what key elements, how they're connected, what you need to do, just like our experimental practices, how to design experiments. So you need to explain to machine it all. And I just want to show bits of this system. So I will focus on hypotheses, because in philosophy of science, for a long time, it was considered that it's something what you cannot automate, so only humans can do it. And to enable this hypothesis generation, so you need to go out of system, out of what you already know. So you cannot use conventional logic like deduction. You need to use something else. So Adam used abduction. So there are other logics that you can use, but you need to go outside of the system. So to have these guesses and then try to see if some of it makes sense or not. So this is just a very tiny fragment of yeast metabolic pathway, so it was all represented in logic. It's only a fragment, so from previous talk you got an idea how biology is complex. We are working on a cell level, but even cell we understand very little about many things. But all what humanity knows, so what we could find, we encoded in first order logic, put it into robot, and robot was reasoning like, if this link remove, or what's this link for, and try to reason, and it outputs 100 hypotheses, possibilities, try to reason what makes sense, if cell still will be alive or what. Then it design experiment to test it. And yes, voila, we had some interesting results. But another part is to formalize science. Again, not any science, but just experimental science. And that was actually very difficult. So first we reflect how we are doing it. So in that concrete example, it was like more than 10,000 different units linked together, because ultimately the only data you have is some measurements, and to make conclusions this gene has that function, it's not trivial. So again, focusing on hypotheses, so like you want to test hypothesis that this particular gene has that function, but you actually cannot put gene into well, or you cannot measure function. So you start doing some inferences. What if we replace it, so use some proxy, if we use something with this gene knocked out, and if we put metabolites, and so you go deeper. So biologists do it just normal practices, but when you try to explain it to computer how to do it, you really need to think. So what steps were taken? We actually very rarely experiment with something what we make conclusion about. So our conclusions are not always accurate. So then you have to go back. So it was very interesting. First try to automate it, and then also reflect on how humans are doing science, especially experimental science. And again, just it's a schematic view how everything was linked, because one hypothesis, you design several experiments, they can have different results, you run all sort of machine learning after that, try to put it all together. And I just wanted to show you our current project, so what we are using such systems for. Right now we are working on projects that is called Action on Cancer. So it is a robotic laboratory, but with all this elaborate software. It has a lot of machine learning tools, it has system biology models, simulators. Again, it's using external data, it's producing its own data, it's using cancer models, genetic information. And again, so it's trying to first modify these cancer models for individual patients, so using individual genetic information, but then it tries to also generate hypotheses. In this case, it's working with drugs. So cocktails of drugs, because if you give one or two drugs, organ is very quickly developing resistance, and so because again metabolomic and signaling processes are so complex, it's clever, it will find ways around. If you block something, it will find ways around. But if you use like 5-6 drugs, and if they're tuned for individual genome, because cancer is very, very individual for patients, so it's very difficult to use this generic conventional. So if you want to have better results, you need to go on really personalized level. And when you need to test like 5-6 drugs, work on this combination, so yes, it's combinatorial problem. If you do it in a lab, we just don't have enough cells in our blood to run all this experiments. So this is a justification. When you need such system, you first do reasoning based on all what we know, with all these gaps, contradictions, but the best what you can do, output some plausible hypothesis what should work in this situation. Then you can do some simulation, again, computational, come up with several hundred hypotheses that then you can automatically test. So that is a cheaper way of doing it using robotics. So this is work in progress. And some reflection on it. So the system is extremely complex. If to put together the state-of-the-art robotic lab and the complexity of software, and even given this, in the best we can do like 3 cycles of refinement after producing all experiments results, reflecting what it means and trying to improve underlying model. And to have something of real value and reliable, you actually need thousands of such experiments, and no system can do it yet. But it's also very difficult actually to connect machine learning tools with robotic equipment. So when machine learning can directly communicate, like, let's test this, and I want to check if this makes sense or not. And anticipating questions, so I don't think such systems will replace human. As you see, at the best they can automate some science, some experimental driven science, but it's important part of science, and if it can be automated, it will be of great help. Humans still have distinct advantages in many areas. Hopefully we will retain it, but ultimately the best way is to work together, take advantage, and really work as a team. And then maybe we can make a faster progress. And another point I would like to make, yes, so far it's quite modest discoveries like gene function, improved cancer models, rediscovering laws of physics, so, but where it's all going. So Professor Kitana set up a challenge to create an AI system by 2050 that can discover something worth of a Nobel Prize. And we are participating in it, so the future will show. But in any case, so Kitana Sensei actually in the past set up a robot challenge that team of robots will beat best human team in football. They didn't do that, but it stimulated robotics so much. There was so much investment and excitement. And hopefully this new challenge will play a similar role. And who knows, maybe it really will happen. So thank you to our funders, and thank you for listening.
Thank you very much for that. That was really interesting. Is there any questions?
Sure. Thank you for your presentation. Just a quick question. What's the difference for you between data and knowledge?
Yes, it's a good question, and in different textbooks you actually can find different definitions, but people who are working in knowledge representations, they have very clear idea. So data is facts. Knowledge is when you go level up, it's like rules, relations, ultimately better if you have models. Better if you have executable models, so you can put something in, get something out. So this is knowledge. And I would like to add to it. So a lot of knowledge you can discover directly from data. If you have a lot of data, you can discover these rules, you can construct models. But why don't represent it immediately as knowledge if we already know it? Why? It's very inefficient way. It takes a lot of energy. These neural networks, they are destroying the planet. And you actually can encode a lot what we know in quite compact way. And you can reuse it. And many I don't know, a lot what we know actually is not in the data. Just an example, I like my collaborator gave this example, like they were modeling ecological systems, and you can have a lot of data, and you can discover from data that bear has between 2 and 5 cubs, and if it's more north, it's less cub. But why bother if we know it? Just encode it as a knowledge. So you can extract it, but you also can just encode immediately. And you can encode a lot additionally what is not in the data. That is why it's more powerful and promising.
Okay, thank you. I think we'll have to draw it to a close. Well, I want to thank all the speakers again for keeping to time and giving some brilliant talks.